Okay, integrated rate laws. So we've been working with rate. We used experimental data to figure out a rate law. And I mean, so far, and those were your differential rate laws. So far we've been comparing, you know, concentration to, you know, concentrations to actual rates. These integrated rate laws are going to compare concentration to time. So like how does the reaction run given a certain period of time? Okay, so we have first order, second order, zero order, then we'll do like a short little blurb on rate laws that are pseudo first order. I'm more interested that you learn your first, second, and zero orders. That's kind of the best place to start. Well, it has to pretty much do with the exponent on. We'll look at it. So here, for example, here's two versions of your integrated rate law for your first order reaction. I would hope by now you're able to mathematically go between those two. Could you turn that first one into the second one? If you can't, make sure do what? Ah, well, you do, but if you have so you can either get rid of it here and switch the order of the left side, or if you take the negative of a natural log, it just takes the fraction on the inside and flips it. And so if let's just say I do it here. So I can do that. Do you know the step to take from here? Do you remember your identities of logarithms? Yeah, so again, I would suggest you go back and review some of your logarithm identities. So if you have an identity is if you have log of x minus log of y, that equals the log of x over y. So then this becomes something else to keep in mind. So you see your graphs here. Remember we talked about this in your lab. The way you know what order your reaction is look at the y-axis. You see how this one is the natural log of concentration, and you get a straight line? That's first order. And so, of course, if you think about it, let's take this one here and reverse the order of the right-hand side. Now look at that equation. What format is that in? Yep. So of course, the slope of your line is going to be your value k. Now, the slope of that line will give you, I mean, it's going to be a negative slope. So you have a negative slope, you put that into negative k, and you actually just get your value for k. Actually, hang on a second. Oh, we did it there. Did I miss? Am I missing a page? Oh, no, there it is. Okay. That was actually, all right. So then the question is, where does the integrated rate law come from? Can we figure that out? Probably is correct. I would say it's more like definitely. But by the way you said it, I'm guessing you don't wanna, because you know where this is going. Okay. It's like, yeah, we can. I don't want to do it. But since since I really enjoy mathematics and I know it causes y'all pain, it's like a win-win. So we're gonna figure it out. Okay, so what we know that we have, and so what we're looking at here is a reaction like that. Okay. Now, do you see how the exponent on that right-hand side is a one? We don't write ones. That's why this is a first order. The exponent will tell you the order. Little question for later. What is any number raised to the power of zero? One. So that'll come in helpful later. So since this is a first order, now what we're going to want to do, okay. We're going to want to evaluate this on tiny little scales. Who's seen this kind of idea, this definition before? What does it mean? Yeah, so as your delta t gets smaller and smaller and smaller to the point where it's almost zero, it's infinitely small. So that means that every single point is going to be an instantaneous rate, or it's going to be okay. So now we can split this up. So what we're going to do is we're going to get all of your concentrations of A on one side, and we're going to get everything else on the other side. So I'm also going to start using primes because when you use limits, you can't set limits that are the exact same thing as what's inside the equation. So in physics, you use primes to just kind of say it's something else that will be filled in by the limits. So what we're going to have this, which when you can do separation of variables, it's the easiest differential equation to solve. So you're happy when you can do it. And so does anyone want to take a guess now why these are called integrated rate laws? Yeah. So we have limits from your initial concentration of your reactant to some future concentration. Now I'll explain this in a second. Constants, just like in a sum, can be pulled out in front of the integral. Because that's what these are. These are infinite sums. So, we've been using that sigma. So if I had something like an infinite sum ends up being an integral. Okay, so this is super duper easy because you see a few identities. First off, anytime you have the integral of just a differential, you just get the letter inside the differential back because that's what these are. These are antiderivatives, or reverse. And so then you also see an identity because if I have this is an identity for natural log of x. Now, I put the integration constant in there because I technically set this up as an indefinite integral. And I know at some point there will be a mathematician who watches one of these videos and is going to go put the integration constant in there. So let's just try to not give them an aneurysm. We're not really going to worry about that because we actually have limits, but let's just not give our math friends, let's not give them migraines. So we'll just go ahead and put the integration constant in there. So what I'm worried about, what I'm more interested in is that definition of your 1 over x dx is defined as your natural log. That's an identity. So one of the keys when you're doing physics, one of the keys to doing calculus is you do a bunch of algebra till you get the equation in a form that already has a solution. And you go, oh, now I know the solution to that. I mean, you can integrate and change limits and do parametric equations and change, like spatial geometries back and forth, but why not just leave that to the math people because they've already done it? Now, so I know that this left side is going to come out to be and I have to evaluate it from the initial concentration to the future concentration. On this side, I'm going to get negative K. And so again, your integral of just your differential, I'm just going to get that back. It's just the reverse of it. And I have to evaluate from time 0 to time t. Your evaluations are just differences. So that's on the left side, you're going to get so that's how you evaluate. It's just a difference between the two ends. And so you get back to which of course gets us back to the first order integrated rate law. And yeah, I know a lot of people don't want to do the math, but we are going to push harder and harder all the time because now so far this group, you guys have been more prepared mathematically than some others. So that's kind of nice to see. But there's just across the country, there seems to be a massive fall off in mathematical education. And it's a little disappointing. It's an entirely different form of logic that a lot of you are just missing out on. It helps you problem solving in the future. And a lot of you want careers where you have to solve pretty big problems. So a little bit of mathematical logic isn't going to hurt you. When you get into physics, what we're going to do is we're going to practice actually modeling systems. So it's like, here's what's happening. Can you model it mathematically? Can you solve it? Because eventually, once you're all done with your schooling, you're done with your graduate school, well, I know we have different mixes in here. We have some pre-med, some pre-vet, some pre-dental, but let's just use pre-med as the example. Someone comes into the emergency room, they have 5 minutes left on their life clock. Solve it. Okay, well, if you can't model it and solve the situation, they're going to die. So we try to develop that logic. Also, mathematics is really, really important for anesthesiologists. That, for example, is where you start bringing back in your significant figures. For some areas, significant figures not going to hurt you that much. Anesthesiology, you're going to want them. You're going to want to know your uncertainty in your anesthesia. Not necessarily. I mean, but the thing is, if you have the ability, also keep in mind anesthesiologists make a really, really nice paycheck because they take on some extra liability. Their math has to be more exact. And so with those skills comes, paychecks come from those skills. It's kind of like, let's say you were building a bridge. As long as as long as the way you built it passed force tolerance, you're fine. However, significant figures really matter if you're building a nuclear reactor. Your bridge will stay up as long as you pass tolerance. If you don't get the significant figures right, you have a nuclear reactor that will either not work or will go into thermonuclear meltdown. So there are places where it matters. You just have to kind of judge your own career path, and if your career path is one of those. But in the health professions, I don't know how you end up in certain careers. Like I think, like for example, I think podiatrists are great. I don't know how you end up there because I don't think anyone comes into college going, "Man, I love feet." Like I don't think anyone does that. But so my question always was, how do you get there? Did we do? Yep, there it is. Okay, so each reaction is going to also have a half-life. Okay, now if the math was upsetting, I'm sure most of you can feel that. But half-life. So that's the time required for a reactant to be decreased to 1/2 its original value. Okay, so it's going to be at T1/2. You're going to have 1/2 A0. Okay, so you can just take your integrated rate law and you can say, well, what if I'm going to write it back out. Okay, now I'm going to substitute in since I've made that substitution, we're now at T1/2. You see that those two are going to cancel out. I'm going to go ahead and write this. I want you to tell me how I got there. How did I get there? Mm-hmm. When you have a fraction in the denominator, what happens? It flips. So your fraction in that 1/2 in the denominator, the 2, will actually then come up to the numerator and you have 2/1. What year was it in school when you guys did fractions? Has it been a while? Yeah. They're coming back with a vengeance. Now, we could always go into the more advanced work of a mathematician named Ramanujan, and we could go into extended fractions. No, no. Ramanujan was a mathematical genius from India.
Yeah. I see that.
Yeah. But you like that guy? You thought his name was a Holiday. You don't know who that guy is.
That sounds similar.
Anyway, he was a mathematical genius. He was able to take a basic middle school math textbook and extract from it this whole idea of extended fractions. He also had one of those memories where people would go square root of 5,260, and he could do it like that. It was amazing what he could do. Mm-hmm. So now, if we actually want our half-life, so then, of course, the way we can abridge this, you notice up here we have 0.693 over k. What is the natural log of 2? You can either do the Tim Heath method and do it in your head, or you can use out your calculator. All right, natural log of 2. Nope. There you go. And so this ends up giving you the half-life for your reaction. So again, each one of these orders is going to have a different half-life. You'll have a couple of options. You can either memorize the half-life equation for each one of them, or you can know that at T1/2, your concentration of your reactant is 1/2 the original concentration. Plug it into your integrated rate law and figure out what the half-life is. And I know that we have some people in here who are more of the biology brain. Trust me, you'll feel a lot better when you get to organic chem and biochem, because that's more like, here's a cycle, learn the cycle. Which, I mean, still can fail you, because how many times if you're like, I got the Krebs cycle down, you sit down for an exam, you're like, I can draw the circle, I forget everything else. Yep, that's it. That's exactly it. Now, I heard someone say one time, and I want to know if this is true. Someone said the Krebs cycle, something about not having enough, dying of thirst or something like that is not having enough water in your system to run your Krebs cycle. Okay. Or a hangover is not having enough water in your system to run your Krebs cycle. So technically dying of thirst would feel like the hangover that finally killed you. I always wondered if that was true. Let's not. You can find that out in the book. You can actually look that one up. All right, so let's look at an exercise. So let's see, we have a generalized reaction of A becomes B. At a particular temperature, you have an initial concentration of A of 2.0 times 10 to the negative second molar. Concentration versus time data was collected. In the plot of the natural log of A versus time resulted in a straight line or a linear plot with a slope of negative 2.97 times 10 to the negative second inverse minutes. Let's see. Yeah, for some reason this book likes to use minutes, but whatever, we'll do that. Well, I changed it to seconds because it bugged me. Seconds is the SI unit. So if you get a problem like this, I'll probably tell you change it to SI units. Determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. Can you do part A? Read that problem very carefully. Yeah, we do. So since we know that, the rate
Because it's a straight.
natural log of A versus time. That's your rate, that's your first order. If you get a linear plot from natural log of concentration versus time, it's first order. If you get a linear plot or a straight line from the plot of natural log of concentration versus time, your natural log is on the y-axis. That is going to be first order. It is. And you had to figure out which one was the most linear. So that means that your rate law is that. Now, what's the integrated rate law? So again, I showed you how to derive the integrated rate law. Maybe more of you just want to kind of remember what it is. There you go. So your integrate, since it's first order, you just pick out. I don't really care what order you write this in. You could do the fraction in the natural log. This is a version of it. Any version of it. It's the first order rate law. Okay, so that's your integrated rate law. What is K? Your rate constant. Kind of. Which way does this graph slope? Down. So that's going to be.
Yeah, so it would be.
Your rate constants will never be a negative number. You got to look at your graphs and say, well, I mean, the slope of this line, then I got to make it positive. So it'd be 2.97. That's your rate constant.
It says on here, the right side, it's natural log of A and subscript 0. What is that?
Oh, yeah, subscript 0. Sorry, I forgot to put that in. Your 0 is your initial concentration. Where the reaction starts before the reaction starts to occur.
So
like you remember, like, well, you've done reactions where you put in like 0.5 molar HCl. That'd be your initial concentration. Same thing. Just as long as you choose one of the forms of the first order rate law. Now, the minutes bugged me. So I said, well, K going to be 2.97 in the native second minutes. It really bugs me when textbooks go outside of SI. Not sure why, but oh, sorry, that's minutes to the -1. So that means minutes is there. There we go. Now we're in SI units, which makes sense because remember, each one of your rate laws, the order is going to dictate the units on the rate constant. Again, if you ever see a rate constant that's just inverse of time, usually like inverse seconds, and they say, what order is this reaction? It's always first order. So again, you can look up tables of that. What are the units of the rate constants of the various orders? And you should be able to tell me what the order of the reaction is based off that. So inverse seconds for the rate constant is always going to be first order. Okay, part B. Calculate the half-life of the reaction. Again, I showed you how to figure that out, or you could just remember Yeah. Now here's a question. How do I get seconds as my units for that? What does s to the minus one mean? In the denominator. A negative exponent means it's in the denominator.
But it wouldn't move to.
Oh, yeah, it would. So what you would have is one over s goes to seconds. Yep. So you're seeing that your assignments for this really shouldn't be that difficult. I'm just showing you the derivation because like I said at the beginning of the semester, I don't just say, here's an equation, memorize it. It's kind of, it's important to learn how to actually figure things out from first principles instead of making asinine assumptions and just saying, well, I don't know how we got there or why that is the way it is, but let's just pretend, let's just believe that it is that. So again, you don't have to reproduce the calculus, but we are going to figure out where things come from. Okay, how much time is required for the concentration of A to decrease to 2.5 times 10 to the negative third molar? So remember, your integrated rate laws compare concentration to time. So if you're asked how much time it takes to go from one concentration to another, your mind should go, oh, this is an integrated rate law. Okay, well, I know what that integrated rate law is. So to drive home that all like these different formats for the integrated rate law are the same. For this one, I used, so we're saying the time is what? That's what we're trying to figure out. So I used yeah, so they're both concentrations. The A is your concentration later and later. Your A0 is your concentration at the very beginning, your initial concentration. Is it not supposed to be? Oh, because I forgot to put a negative sign on the KT. Yeah, so let's see here. Your T, you divide through by negative K. I left the units out of the natural log because it's just m divided by m cancels out. So you get a healthy little calculator exercise here. So see if you come up with 4201 seconds. Does that sound like a really, really long time? It's about 70 minutes, I think, but is it 7 or 70? Okay. It's like I could have missed a zero too. So see if you can get your calculator to give you that 4201. Let you know if you're doing well with your calculator or you need some practice. You got a negative? Yeah, but do you remember the negative out front?
Oh,
Yeah, so it's a negative of a negative. So remember, the natural log or the logarithm of any number less than one will come out negative. Starts to really blow your mind when you're like, the natural log of 2 is 0.693. The natural log of 1/2 is negative 0.693. Please. You're like, let it work. Let it work. When we get done with this, that's first order. We have 2 more to go.
Nice.
So do that division first. The 2.5 over the divided by the 2.0, then take the natural log of that number, then divide that answer by the 4.95. Yeah, you can do that too. You know, 0.0, so 0.0025 over 0.02. Needless to say, we need practice with our calculators.
There we go.
Nice. Starting to think our campus needs like an intramural combat sports,
That's like. Really easy.
like intramural UFC, like mixed martial arts, like just like go in, take your frustrations out on someone else. Like, go in for like the championships, like 3 exams today. You just- you could, you know, don't make like a mask with the face print on there. Go here, wear this. I always like to imagine that I am one of those teachers. Because it just brings me joy. Yeah. Yeah, I don't get paid enough to not enjoy it.
You'll find a little things.
You do. Yeah. Remember, a scientific education, you're doing it right if you spend half your time in the bathroom resisting the urge to cry. Yep. If you're already there, you're on the right track. Made me mad when I was in graduate school because the women's restroom had a sitting area with couches and stuff, and I was like, I want couches. I'm like, I want an area where I can go sit where no one can come bother me. Like, it's stupid. I want couches, but no, we didn't get them. My advisor in grad school offered to buy us all cots so we could just sleep in the lab and do research 24 hours a day. I was like, dude, you're nuts. Uh-huh. He goes, think of how much work you'd get done. I'm like, no, absolutely not. All right, so we are on to second order rate laws. Okay, so again, same generalized equation. A becomes products. Your second order rate law, again, you see the exponent, the 2 tells you it's second order. And so then your integrated rate law is going to be there at the bottom. And let's see if we can figure out how we get there. Okay, well, again, your graphs. Do you see over there on the right your 1 over concentration versus time? If your straight line comes from that, it's second order.
Wait a second. You talking about the second graph?
Yeah.
What's the second?
You see how the y-axis is 1 over concentration of your reactant? If that 1 over concentration of your reactant versus time gives you the linear plot, it's second order.
And the first order was.
Natural log. Natural log. So 1 over is your first order, or your second order. Natural log is your first order. And then just your straight concentration versus time is your 0 order.
Whoa. First one, 0.
So if it's just concentration versus time gives you a linear graph, it's 0 order. Natural log of concentration versus time is first order. 1 over concentration versus time is second order. Yep. You're looking for the linear graph.
0 was.
Yeah, concentration versus time.
First was just.
Natural log of concentration versus time. Is 1 over concentration versus time. And so when you find your linear plot, that tells you the order of your reaction. And I do like to stress that because on standardized exams, they'll give you a graph and they're expecting you to look right at that y-axis and know first order, second order, or 0 order. And that can actually help you, get through some problems faster. So let's take a look and say, well, if I take this and turn it into a differential equation, here's where we are. Now, again, I'm going to separate variables. I'm going to get now that right side, we shouldn't even have to integrate anymore. So it's going to come out the same way every time. You saw how to do that last time. You know it's going to come out negative KT. But let's look at that left side. We'll set this up and then solve it next time. Now, this is not going to be the natural log. It kind of looks that way, but it's not 1 over A. It's 1 over it's 1 over A squared. So it's a little different. So the way we want to do this is we want to make it easier on ourselves instead of dealing with 1 over A squared. I just want to turn this into, then I'm going to use my prime to denote something that's a placeholder. That's the integral I want to solve. Because next time, what we're going to do, what you'll see is that if I have any integral where I have an exponent of n, in this case, my exponent's a -2, your formula for this is going to be 1 over n plus 1 x to the n plus 1. So that's your formula for your integration. This is called the power rule. Okay. I feel I've broken a few brains, probably made your heads hurt. We'll call it for today.
Well, we're at some, well, a bit of tennis.
Yeah. Oh, okay, yeah.
That is right there.